And my name's Adrian Jackson from the University of Edinburgh, from EPCC at the University of Edinburgh. I'm going to talk today about our experience with using the A64FX processor for scientific applications, common scientific applications. And so this is actually a sort of continuation of work that we've been doing for a couple of years now, looking at ARM-based, or should that be NVIDIA-based processors going for use in computational simulation applications, really looking at how easy is it to move codes, large-scale simulation codes between a range of systems. And of course, we're interested in that in the UK, not just for ARM and not just because new processors, but we're always looking to see if we can get the best systems for our scientists to use for their simulation work. And of course, Fugaku is a great example of a large-scale HPC system which provides very, very high performance. So we're always on the lookout for what applications can we use on what processors. And that's because whilst we're very interested in the latest processor, what's important to us is sort of evaluating how easy it is to exploit and what work people are required to do to get up and running. What level of codes can we take across and how much work is needed to do that. And so there's a growing range of production ARM-based server processors out there. Kicked off actually a couple of years ago with the Thunder X2 ones, which have been used now for a couple of years in large-scale systems, but also a real range of interest in other processors like the Amazon Graviton processor and of course the A64FX processor. And the A64FX processor, I probably don't need to introduce to anybody in this workshop, but it's very interesting on a number of ranges. One, because it was designed with these sort of workloads we're looking at here in mind, so computational simulation, scientific applications, machine learning codes. And so it's always great to see that kind of co-design and the kind of performance you can get from that. But also because it's the first processor that we've been able to play with that uses the ARM SVE vector instruction set in anger, and it has this high bandwidth memory on the processor as well. So it has a high bandwidth to memory, 8 gigabytes of memory per quadrant, per group of 4. There's 4 quadrants on the processor, each with 12 cores on it. And so in a number of different ways, it's a very interesting chip for us to look at for applications because at least theoretically, it should address a lot of those memory bandwidth issues we have for a lot of applications we have, but it also has the high vectorization we see commonly on Intel processors, and it's designed to do well, hopefully on computational simulation codes, which is what we spend our time running. So that's why the processor looks very interesting from our perspective, but also we know from many years of experience with these kind of things that it's not just performance which you're interested in, it's what's the ecosystem like, what software is around it, what libraries are available, how easy is it to get your code up and running, what are the compilers like. So what we were looking for really here was to take some work we've already done looking at the Thunder X2 systems, particularly this HPE Apollo 70 we have in Edinburgh, and there's a few of them around the UK and globally, where we could see that there was great performance with that processor, and there was quite a nice software ecosystem around the ARM processor there with performance libraries and compilers. And look what that looks like for the A64FX system as its equivalent. So we were interested in looking at application performance at scale, so multi-node runs, not just single nodes, but also particularly evaluating porting and software ecosystem maturity, and looking to see, how other places where this works better than other places, particularly we have good Fortran support, because we still in the UK have a very large number of Fortran codes, which a lot of people would call legacy codes, but 75% of our main system codes on our big systems are still running in Fortran, so we need good support for that. So the work we were doing was to take our access to the A64FX processor and run a set of codes and then benchmark across a common set of systems, including this Archer system is our old Cray, which is still our main system that we're using in the UK, but soon to be replaced by an AMD system. And then a number of other newer systems, Intel Broadwell, Intel Cascade Lake, and Thunder X2, Marvel Thunder X2 processor system, and see what kind of common performance we got across the range. And for those of you who are interested, you know, we looked at a number of benchmarks and full applications, because whilst sort of mini apps and mini benchmarks are interesting, we often find that the actual real issues in performance don't come along until you try and run the full application, and then you see different behavior than before. So we looked at a range of codes, and all the libraries and compiler flags we used are in the paper. I don't expect you to be able to read this, of course, but it's in the paper online for those who want to know a little bit more detail about what we were doing here. So without any ado, I will go on to the benchmark results we had. So there was a number we looked at, starting off with HPCG, and I should say up front we have you know, quite a skew in the kind of applications we're interested in here. So you'll see quite a number of CFD applications and quite a number of applications where conjugate gradient is the sort of dominating benchmark, dominating computational kernel. And that's partly due to the applications we had access to, which we could easily benchmark, but also we actually see quite high usage on our systems for these kind of engineering applications, CFD, and applications which are dominated by these kind of maths kernels and math libraries. So, you know, we're not going to claim that these benchmarks we're talking about today and in the paper are 100% representative of all codes across the systems, but they're a reasonable subset of the codes we see heavily used in our big HPC systems. Anyway, HPCG is a commonly known benchmark, so it seemed like a sensible place to start, and we ran this across our the systems we had access to see what it looked like. And we can see from this table at the bottom here that the A64FX is actually giving us you know, overall the best performance out of all the systems we've looked at there, with a peak performance of 38 gigaflops for a single node HPCG run. And so this was pure MPI HPCG, and all the cores and all the nodes we used with sort of full node runs. But that's where we typically saw the best performance across all the systems. So that's not a disadvantage in any systems there. Interestingly, we've got a couple of different results for the two systems at the bottom, the what we call EAHPC NGIO system and the Fulham system. Fulham is the Thunder X2 one, and EPCC NGIO is the Cascade Lake system we have access to. And the two different results we have there, optimized and unoptimized, are where we compared running the HPCG software, the unoptimized version from the sort of main source repository, which you can just download and run yourself. But also Intel and ARM have their own optimized versions of HPCG where the performance libraries have been suitably linked, but also some optimization on some of the key computational kernels has been undertaken. And so we can see there that actually the vanilla HPCG is a fair bit slower than the optimized HPCG on those two systems where Intel and ARM have put work into it and optimized the core computational kernels. It really has made a significant difference to performance there. Why are we interested in showing that? Well, on the A64FX system here, we're using the default HPCG, which we just downloaded from the main repository. And so whilst we're getting great performance, it would suggest that there should be potential. I'm sure people actually, I'm sure the scientists at RIKEN or at Fujitsu have already done work on this to improve that 38 gigaflops per node, so that this peak theoretical performance here of 1.1% of the peak flops in the processor goes much closer to what we see on systems like Archer or on the optimized Intel and ARM systems at the bottom here. So we get good performance on the A64FX out of the box without having to do anything apart from specify a set of compiler flags. Sort of even better than that, when we look going multi-node on the system, actually that good performance is sustained going out to 8 nodes on the system we had access to. So I should have said this was early access to the A64FX was through the Fujitsu early access programs who were running on a Fujitsu A64FX system there. But you can see here that whilst this optimized EPCC NGIO system is comparable in performance on one node to the A64FX, when we scaled up to 8 nodes, we can see that there's a bit more of a gap between them. So the A64FX is showing really quite good sustained performance going out across the network as well, which is great to see. Following on in a similar vein, we have a mini app benchmark called minikab at EPCC, which is another parallel CG solver, but one which was designed so we can play around with the algorithms used and the communication approach used and the decomposition used. It's a sparse matrix benchmark, and we had a look at that as well on the A64FX to see what performance was. And here we can see actually, similar to what we saw with HPCG, we can see that the A64FX has given us a great performance, slightly better than the Cascade Lake system, and quite a lot better than the ThunderX2 base system here. So we can see sort of more than twice as fast as a ThunderX2 base system here. And this, based on sort of preliminary benchmark profiling, would be looks like it's because of the access to the higher bandwidth memory is giving us good performance here, and vectorization is giving us good performance here. So the use of larger vector units on the A64FX is giving us sort of comparable performance to the Cascade Lake, which has similar vector length there. Nekbone is another mini app we looked at, which is of similar kind of structure to HPCG. In fact, it's designed to do similar kind of things, but it's a reduced version of a NEC 5000 application. Again, we had a look at that across the systems. We can see here from the table at the bottom that out of the box, we're getting better performance on the A64FX than, considerably better performance of the A64FX than the other equivalent systems of ThunderX2, one of Fulham, and the Cascade Lake, one of EPCC NGIO. And so, that's showing great performance out of the box. But the interesting thing we saw here is actually playing around with the compiler flags here. Actually gave very significant performance improvements on the A64FX. So if we compare the gigaflops column to the gigaplops column with fast maths, we can see that the A64FX is almost going twice as fast when we enable a couple of compiler flags to use the fast maths options in the compiler. We don't see the same benefits on the other systems. And interestingly, actually, the EPCC NGIO and the Intel Cascade Lake goes slower if we turn on some of the fast maths optimizations in that library, in that compiler, sorry. Of course, we're comparing different compilers here. So we're comparing Fujitsu compilers to the Intel compilers to the ARM compilers. So there's a lot of stuff going on here, but it was interesting for us to see that for this application, a little bit of playing around with the maths libraries and the compiler options gave us some really significant performance improvements for the A64s. I mean, there was no code change involved in here. It was just you used the correct flags. So we've got a bit of work to do to work out what the difference is between these two results and why it's significantly faster here with the -k fast flag, if you're interested. It's nice to see this performance here. And interestingly, this performance of 312 gigaflops per node is quite similar to what we see to a comparable GPU system, which this benchmark has been ported to. So comparable NVIDIA V100 benchmarks are around 300 and something gigaflops a second. So we can, for this particular benchmark, for this particular configuration, we can see similar performance on the A64FX to the Intel's top-end GPUs, which is nice. And again, we had a look, so as well as just looking at single point benchmarks, all the work we've done here has been looking at, you know, different configurations of benchmark, different number of cores per node. You know, some of the results I haven't presented, but, you know, looking at how does hybrid versus, so OpenMP plus MPI look compared to pure MPI and these kind of things. Yeah, but so just as an example of that, we were also looking at performance when we scale up across the number of cores in the node, and you know, where the sort of sweet spots are there. But we can see that the A64FX, which is this top purple line, the A64FX fast, is, you know, significantly faster across the board. Without those compiler flag optimizations, we can see actually that the performance isn't as good as the Cascade Lake system until we get up to the larger numbers of core counts, and then we can see that the additional memory bandwidth we have there, I think, is giving us a performance benefit above and beyond what the Cascade Lake has, because it's saturating at about, you know, the 24 core mark on the Cascade Lake compared to scaling up to a full 48 cores on the A64FX. And then, so those were for mini apps. When we start looking at, then we were also interested in sort of full application code. So sticking with the CFD theme, we had a look at a code which is run locally called COSA, which is a CFD code, but it's a harmonic balance CFD rather than a time domain CFD. Not that that really matters, but it's just a slightly different science domain. Interestingly, so it's Fortran, but Fortran with clear pointers, and this can be problematic moving between systems, but actually was perfectly straightforward to port to the A64FX. And we can see here that we get actually really quite good performance for the A64FX all the way up to, well, this is, we actually, so the line graphs here are slightly misleading, but we ran on 1, 2, 4, 8, and 16 nodes here, right? So we can see we're going from 8 to 16 nodes. Actually, Thunder X2 outperforms the A64FX, but actually this result isn't quite correct, and I'll go on to see why that is. One of the things that's worth pointing out here, of course, is one of the challenges of going to the A64FX compared to the other systems is the amount of memory available per node. So actually here we can see that all the other systems we were able to run this benchmark on a single node and scale up from there. The A64FX, we had to use 2 nodes because this benchmark requires more than 32 gigabytes of memory, so we couldn't do the single node performance test there. But we could, beyond that, you know, scale up beyond there. The reason why the Thunder X2 looks better up at this high level than the A64FX is actually that we're over decomposing on the Thunder X2 up here because it has many more cores per node than the A64FX. Well, it's got more cores per node than the A64FX. Actually, when we get up to 16 nodes with the Thunder X2 system, we've actually got more cores than we need, and so that introduces some performance differences between the two systems, which means that we get a slightly better performance on the TX2 processor up here, but it's not real. You would never run the application at this number of nodes up here because it's not an efficient way of doing it, even though it's slightly faster. So in reality, we can say that up to this point, up to the 8 nodes where it makes sense, where we're not over decomposing, but the A64FX gives us, you know, better performance across the board. Not hugely better performance, but it is outperforming the other systems here. And even if we look on a per MPI process basis, it's exactly the same data, but rather than looking at number of nodes, we're looking at per MPI processes. We can see that on a per MPI process basis, the A64FX is outperforming. Again, you know, once we start looking at nodes with systems with different number of cores per node, then it becomes hard to compare across MPI processes. And actually you can start to see in these scenarios, one system looks better than the other, but it's just because you're using more nodes. Here we can see that the A64FX is still better across the board, regardless of the number of cores we're using on equivalent number of MPI processes. So I'm swiftly running out of time. I won't take up too much more, but you know, up till now we've seen that the APC64FX is giving us great performance across the board. There are a couple of applications that we looked at where it was the same wasn't true. And so here's one called CASTEP, which is another Fortran code, but this is a materials code, materials science, DFT code. And actually we can see that on this here, A64FX is giving us good performance, but not quite as good as the Cascade Lake. So the Cascade Lake is about 27% faster than the A64FX here. And we can see that if we look at the scaling, that, you know, scaling out, this is inside a single node still, but you can see there's a reasonable gap between the green line, which is the A64FX, and the red line, which is the Cascade Lake processor. But the A64FX is still outcompeting the Thunder X2, not hugely, but it's still outcompeting the Thunder X2. And likewise, OpenSBLI is another CFD code. It's a C code this time with some automatic parallelization and Python things in there. But again, looking at the performance there, we saw actually on the A64FX, we actually saw, you know, significantly slower than the other systems. And so for this benchmark, the Thunder X2 and the Cascade Lake were very similar performances, but significantly faster than both the Broadwell processor and the A64FX processor. So, you know, the code gets there and we can run it, but it's not giving us the performance we would expect at this point from here. When we started looking into why this is, and I think actually for this and for the CASTEP's code, there's a little bit of stuff going on in the MPI, which is meaning the performance is not what we would expect there. So actually you can see benchmarking this OpenSBLI code on a single node of the EPCC NGIO system, where it was giving us good performance. We can see, I don't expect you to be able to read this, but we can see that actually most of the time for this code is being spent in the MPI, sitting in the MPI there. And actually it's not vectorizing very well at all. So we've got about 2% of this running in vector mode. There's a fair bit of floating point and memory stuff, but it's not vectorized floating point and memory stuff. So it looks to us here that both the CASTEP and the OpenSBLI, where we're not seeing the same performance, there's some scope for optimization there, either in the MPI implementations or by making sure that the vectorization is giving us good performance. And so I think, you know, there's some scope there for us to actually do some work on these codes on the A64FX and then get the performance up to. And so I have spoken for too long, so apologies, but you know, our takeaway from this was the A64FX and actually all the ARM processors we've played with, so A64FX and the TX2 are giving us great performance for a range of codes we're looking at here. What's important to us is it's been pretty easy for us to port to these platforms. We haven't had to do anything to the codes really. The libraries we need to do there, the compilers worked. There are some codes where we can see there's going to be some scope for optimization, but I think, you know, as with any new technology, that's always going to be the case. And we've got some, you know, really interesting places to start and go forward and look at performance. So with that, I'll finish my presentation and I'm happy to take questions, but or maybe later on, given I've used up more than my fair share of the time. So apologies for that.
All right. Thank you, Adrian. I was going to say, I know actually John would like to, has a question to ask. If it's the ones in Q&A, you can type up the answers. Go on.
Yeah, thank you very much. So but I'll just actually defer my question. So we have a question here from from Dr. Seto, who asks, for multi-node evaluation, are you using the FX1000 with TOFU or the FX700 with InfiniBand?
So this is with the TOFU network.
TOFU.
Yeah.
Thanks.
And I can answer the other question on how many more cores do you get at 16 nodes? So I'm assuming this is a question about if we compare the Thunder X2 to the A64FX, then there is well, my maths is going to let me down here, but there's 12 more nodes, 12 more cores per node, and so it would be 12 times 16 more cores at the no, my maths is letting me down there, isn't it? There's not 12 more cores per node. There's whatever 64 minus 48 is more cores per node. So effectively, the benchmark that I was looking at, where we had more cores than we needed, when we got up to the 16 nodes, there was 1,024 cores on the TX2 system, but we could only use 800 of them, just because of the way the benchmark was set up. So we had a significant sort of overspill of cores up there. Should never try and do maths live. It's never a sensible thing.
That's great. Thanks very much. All right.